Hello and welcome to Thursday's edition of Cracking a Cryptic, where today I'm going to be looking at a puzzle that has literally just arrived with us. It's called Everest and it's by Clover. Clover is one of my very favourite setters. She is absolutely brilliant. She sent an email in and she enclosed some feedback she's had on this puzzle over on Discord. And this feedback is from some very fine setters with some very odd pseudonyms over there. Oh God, it's Grockles is in fact, of course, Grockles, who says, this puzzle is disgusting. Why do you have to show off like this? It's just rude, which is very funny. Sam Kapperman Lines says, that was an exceptional puzzle. So laconic and to the point as ever. And Tiganus, I want to discuss it without giving things away, but it's hard. All I'll say is that I've solved a lot of killer. It is a one of a kind. So this sounds fascinating. So I've basically I want to do it. So why not today? It may be jumping the queue a bit, but that's fine. I'm also actually I have a sort of romantic interest in Mount Everest. I always used to think I wanted to climb it. I think as I've got older, I've got less brave about that. But I've read many books on the subject and so Clover has named this puzzle. It's hit my sweet spot, let's put it like that. I'm not sure why it's called Mount Everest though. Maybe it means it's incredibly hard, or maybe it means we have to sort of start at the bottom and solve it upwards. I don't know. We shall see. Anyway, I'll read the rules of this one in just a moment. There's only a couple of things to mention. Firstly, Mark and I are going to be back streaming Obra Dinn tomorrow night. That's Friday night, UK time, 10 o'clock. We'd love to have your company. And the other thing, of course, is what's going on Patreon at the moment. There is an absolute multitude of extra content. We've got my solve of the amazing Two Truths and a Lie puzzle by Zetamath. Do have a go at that. You can have a go at that at the link under this video right now. It's an unbelievably good puzzle. Very exciting logical path and not easy to find. So yeah, have a go at that. And what else? Well, of course, we've got the November monthly reward. Well done if you have got through that. It's about 45 puzzles long, and you have to earn your degree in Japanese sum Sudoku puzzles. And many of you, I'm astonished to say, have already raced through your degree. So something of a sort of, there's a lot of prodigies watch Cracking the Cryptic, clearly. Anyway, do have a look at those. You will enjoy them. And if you can get your answer to us, which is the password for the final degree file, you get your answer in by the 20th of November, you'll be in with a chance of winning a prize. So that's all I've got to tell you. Let's get on with this. Here are the rules. Normal Sudoku rules apply. Digits cannot repeat within a cage and must sum to the value indicated. So this is just completely normal killer Sudoku, which is really rare actually on the channel. We don't tend to get too many just normal killer Sudokus, and if we do, they often don't get past the testers because, we get so many amazing puzzles. It is the golden age of Sudoku, as I said yesterday. But anyway, this is normal killer. You can play by clicking the link under the video. Can't remember if I said that, but now I get to play. Let's get cracking. Now, let's get cracking. So do we start? This looks a little interesting, doesn't it, straight away? We've got 26, 36, so those two squares have got to sum up to 9, and that's because of the secret. I only tell the secret to a very few people, but how do I know these two squares sum up to 9? Well, it's maths, that's what it is. We know because of the rules of Sudoku that any complete box of a puzzle, so this complete box contains the digits 1 to 9 once each. Add up the digits 1 to 9, you get 45. Now, if I know that domino adds to 13, and that domino adds to 13, and that triomino adds up to 10, I can add those digits up and get 36. So 45 minus 36 is the 9 that goes into these, and that is, of course, I was about to say that's useless, but it nearly is useless. But it does mean, I'm now thinking about where 9 goes in this box. It can't go in the 10 cage because you can't accompany it with a 1 and a 0. It can't go in those two squares because we know those two squares together sum up to 9. So I can't put 9 and 0 in. Therefore, there is a 9 in one of the 13 cages. therefore, in one direction, this is a 4-9 pair, and that is probably useless. 9 in box 5 is restricted as well. You can't put 9 in a 4-cell 14 cage, because if you try to, the other 3 digits have to add up to 5, and 1 plus 2 plus 3 is 6, so that doesn't work. So in the central box, the 9 is in sort of an empty rectangle type pattern, i.e. it's either in one of these 3 squares, or it's in one of these 3 squares, or both if it's in that cell there. Can't see what that's doing. No, hang on. Maybe I'm not meant to start this and climb. I'm not meant to go through the Khumbu ice fall first. I might have to start at the very top of Everest. And try and negotiate the Hillary Step, or whatever it was called. Because that cage and that cage, I actually know what's in those cages. That's a 6-cell cage. Well, the triangular number for 6 is 21, so this must be 1, 2, 3, 4, 5 and 6. Now 22 is also forced. That's got to be 1, 2, 3, 4, 5 and 7. So we've got an awful lot of, well, I was about to say low digits, but perhaps it's better to describe it as an awful lot of shared digits between those two symmetrical cages. I mean, the grid is symmetrical around the negative diagonal. So what's this telling us? I don't know. 8 and 9 in box 1 have to be in 2 of those 3 cells. I feel like it might be this 14 cage actually, because whatever digits I put in the 14 cage, surely some of those digits at least have to appear in the sort of tail of this cage and the tail of this cage. So we're going to get digits pushed into the 14 and the 16 cage. Can it really be that type of thing we have to think about? Let me just think about this for a moment. I think it feels like this is deliberate to me. So a 14 cage. I'm trying to think about it in terms of the digits that have to be in these 6 cells. 1, 2, 3, 4 and 5 appear in both of these 6-cell cages. So what we can't do, so these little tails here, let's highlight those cells. These tails must contain 5, well, it must contain a 1, 2, 3, 4 and 5, mustn't they? Because if they don't, if we decide that there's no 1, for example, in those yellow cells, then the 1 in the 22 cage will be in those 3 squares, and the 1 in the 21 cage will be in those 3 squares, and we'll get 2 1s in box 1. So the common digits between these 2 cages, 1, 2, 3, 4 and 5, appear in 5 of those 6 cells. Now, a 14 cage could have 2, 3, 4, 5 in it, and that would require us to allocate 2, 3, 4 and 5 into the 14 and the 16 cage, because obviously if this is a 2, 3, 4, 5 quadruple, given we know there's a 2, 3, 4 and 5 somewhere in the yellow squares, it doesn't matter how we well, it will eventually matter how they're allocated, but you can see by Sudoku, therefore, they're going to have to be, or they're all going to end up by hook or by crook in the 14 and the 16 cage. Because if there's a, let's say there's a 2, the 2, 3, 4 and 5 we know must exist in these cells. Let's say the 2 and the 3 are up here. That's a bad choice, actually. Let's say it's the 4 and the 5 are up here. Then there would have to be the 4 and 5 in column 6 in there. And then the 2 and the 3 would be there, and the 2 and the 3 would be there. So 2, 3, 4 and 5 add up to 14. So that would put 14 in 4 of these 6 cells, and the other 2 cells would have to add up to 16, which they could be 7 and 9, or actually they, oh no, they can't be double 8. You can't put 8 here and 8 here, because then that's going to rule 8 out of there. So on this presumption, you would have to have 2, 3, 4, 5, 7 and 9 in the 14 and the 16 cage, but that's probably possible. And of course it doesn't have to be 2, 3, 4, 5 here. It's absolutely possible that there's a 1 in here. And then a 1 will get allocated to one of these cages. Whoa, okay. So I don't feel like I'm climbing this mountain at the moment. I feel like I'm sort of skiing down it. I've dropped off Le Fas in Val d'Isère, and I'm heading down for an epic fail. And I'm not. I don't think I do know what goes in there, do I? So this is 5. This is 5 of this, but well, actually, that's a good question. Is it possible that is it possible there's a repeated digit from 1, 2, 3, 4, and 5 in there? Then that digit would be allocated twice into those cells, but there's nothing inherently wrong with that. Oh dear, oh dear. What did Grockle say? This puzzle's disgusting. It's disgusting, Clover. It's disgusting. So I feel it's something to do with how we allocate digits to the yellow squares. 1, 2, 3, 4, 5. If there's no repeated digit, then those 1, 2, 3, 4 and 5 would end up in those 6 cells as well. Because of course, effectively, between these 2 cages, there are 2 lots of 1, 2, 3, 4 and 5 that we've got. Oh, it's not set, is it? Clover, of course, normally, we know her from the gas puzzles, the genuinely approachable Sudoku puzzles over on the Discord server. And this is not one of those, at least not so far. It's not set, I don't think. Oh, it's almost a bit like yesterday, the Ard van de Wetering. No, there's too many gaps. Right, okay, let's don't think about set. What was I thinking about? I was thinking about the fact that we've got I've got to allocate 2 sets of the digits 1, 2, 3, 4 and 5. Oh, goodness, right. Hang on a minute, am I right about this? Let me just think about this again. 1, 2, 3, 4 and 5. Yeah, that's... Okay, I think I've been looking in the wrong place. I've been looking at these 2 cages. But actually, maybe I should be looking at these cages. Let's highlight those cages instead, because I've got to put some of the digits 1, 2, 3, 4 and 5 into those cells. Yeah, and they're going to marry up. We're going to have like stretched X-wingy type patterns again. Right, hang on a minute. How can I articulate this in a way that's going to make any sense, to me included? Because at the moment, 2, 3. The problem is it is possible for there to be repeated digits into these. What I mean by a repeated digit is it's possible that there are sort of 2 2s in those cells. And that's confusing me about what it means up in box 1. And maybe let's make the assumption there is no repeated digit then. If there's no repeated digit between the yellow cells. Ah, got it, right, good grief. Wow, we have taken our first step towards the summit, I think. Wow, right, okay. So, let us start with this. We know that there must be a 1, 2, 3, 4 and 5 in the yellow squares. And we know that's true because if there wasn't, let's imagine we try and miss the 1 out. We say there's no 1 in any of those squares. You can see there's now a 1 there and a 1 there, and the puzzle's broken. So that's nonsense. There must be, because there are so many common digits, we need 1, 2, 3, 4 and 5, the common digits, to each appear in the yellow squares. Now the tricky thing is whether one of those digits could appear in this yellow segment here and this yellow segment. But let's make the assumption for a moment that there is no repeat. So this just contains the digits 1, 2, 3, 4 and 5 once each, and then a 6 or a 7, something like that. Now if that's true, where do the 1, 2, 3, 4 and 5 go in box 1? And that is a really, really interesting question. Because let's imagine that these squares here contain well, it doesn't matter. Let's deal with the number 2. Let's just think about the number 2. Now, where is 2 now going in box 1? Now, 2 is not going to repeat in its own cage. And by assumption, I've said 2 is not repeating in yellow down here. But we know there's a 2 in the 21 cage, so it goes in there. And that pushes the 2 into the 18 cage. But that logic is extendable for every single digit 1, 2, 3, 4 and 5, because I've made the assumption there's no repeat in yellow. Now that means that the digits 1, 2, 3, 4 and 5 appear in 5 of the 6 cells in the 18 and the 14 cage. Let's do another example just to show you it's symmetrical. If we say there's a 3 in here, but there's no 3 repeated in yellow, then there's no 3 there. There must be a 3 here, so the 3 gets pushed in. So that's what I'm thinking about. Now, if the digits 1, 2, 3, 4 and 5 get allocated to the red cells, that's 15. The other red cell to make the total work, which is 32, would have to be a 17. Now, here is a knowledge bomb from Cracking the Cryptic. You cannot put 17 into a single Sudoku cell. So, we have now learned there is at least... could there be 2 repeats? No, there can't be 2 repeats. Right, sorry, I was about to get confused and confuse myself again. But we're doing well now. Now, so let's deal with that. I said that there must be the digits 1, 2, 3, 4 and 5 in the yellow squares, and I stand by that. And there is now 1 repeated digit because there are only 6 cells. If you're worried about whether there could be 2 repeated digits, there cannot be, because let's imagine we try and do that. Let's put 2 and 3 in both of these sets of digits. Well, now, obviously, I've got too many cells here to fill with too few different digits. I've got 5 cells. I've got 6 cells and only 5 different numbers to choose from. That's not going to work. So there is exactly 1 repeated digit between in these 6 cells. So there's the numbers 1, 2, 3, 4, 5, and one other digit, which is a 1, 2, 3, 4, or 5, but we don't know what it is yet. But aren't we going to have a problem if it's a low digit? Because we now know for sure that every digit in this pack of 6 digits is getting allocated to the 18 and the 14 cage, except the repeated digit. The repeated digit doesn't have to be allocated, because let's imagine the repeated digit is a 2 again. There's a 2 here and a 2 here. Well, now there's no 2 there and no 2 there. So the 2 in this box would be in one of those 3 squares, and there's no reason to have to allocate it to the 18 or the 14 cage. The difficulty comes when you don't have the repeated digit. So the 2 gets allocated there and then up there by force. So this pattern is beautiful. It's incredibly clever and difficult to understand for me. I'm sure many of you are already getting cross with me for not going faster. But yeah, this is perfect. It's actually beautiful. This is absolutely glorious. We have, I think, just summited, and it is sunny, and we can see the view. Because, yeah, I now know for sure that exactly 4 of the digits 1, 2, 3, 4, and 5 end up in the 18 and the 14 cage, because we know that that set of digits is the digits 1, 2, 3, 4, and 5, and 1 repeat. The 1 repeat doesn't get allocated, the other 4 do. Well, if we max out the 4 digits we can allocate to the 14 and the 18 cage, it's going to be 2, 3, 4, and 5, which add up to 14. Therefore, the other 2 cells in the 14 and the 18 cage would have to be double 9 in order to get to the right total. That's the only way it can work. If we allocate anything less than 2, 3, 4, and 5 to these cages, we can't put 10 or 11 into the cells, so it won't work. So we now know for sure the contents of these cages. They are 2, 3, 4, 5, and 9, and there is a 9 in both of them. Oh, and in fact, that's beautiful as well, because then how does the 14 cage work given the options? It must be 2, 3, 9. So that's not got 4 or 5 in it, which means that one does have 4 or 5 in it, along with its 9 to make 18. Here we go. We're cooking with gas now. We are cooking with gas. My very favourite story about Mount Everest, by the way, is a very rude story told by Brian Blessed on Have I Got News For You in the UK, and you'll have to Google it because I'm not repeating it here, but it did make me laugh. Now, let me think about this now. So what does this mean? So now, yeah, okay, well now let's get rid of 6 from here. There's no 6, there's no 7. The repeated digit we know, this is beautiful. The repeated digit we know is a 1, because it must be, because we need to allocate the 2, 3, 4, and 5 to the red cells. So there's no 1 in these cells. So these 3 squares are now 1, 8, 9 triple in box 1. Now we must also, presumably, we know that 2 and 3 are being allocated down here. Now, yeah, let's think about what that means. That means that there must be a 2 and a 3 up there. Because if there wasn't, if we try and put the 2 here, for example, then we know there's a 2 in that square, and there should be a 2 in the 18 cage, which there most certainly isn't. So there must be a 2 and a 3 here. This square is not 2 or 3. This is a 4, 5, 6 triple. This is therefore not got 4 or 5 in it. That's a 2, 3, 7 triple. And this must be a 1, 2, 3 triple. It's not 4 and 5, and that means we no 2 and 3 here. So this is 1, 4, 5, with the 4 5s matching being thrown off up there. This is the 2 3s matching being thrown off down there. Okay, so now we are a little bit closer perhaps to a digit. We've still not got a digit. That's not a 9. Oh, for goodness sake, Simon. 24 minutes. I've not got a digit in a killer Sudoku. This is... Well, this is the scale of the challenge we are facing. So, what now? Ooh, so if that was the 4-9, 13 cage, that would be a 5. If that's the 4-9, you don't get as much of a restriction. Wherever the 9 goes in box 5 now, is pushing a 9 into one of those 2 cells. Unless the 9 is here when it's being pushed into both of those cells. Oh, that's quite cute. So, given the 9 is in one of these positions in box 5, and given the 9s in boxes 7 and 3 are in these cells, there's always a 9 in one of those 2 positions in box 2 or 4. We don't know which one, and it might be both, but it's definitely in one of them, so that square's not a 9, because that would rule a 9 out of those 2 squares and render the puzzle unsolvable. So that square's a 9, which means there's a 9 in one of those 2 cells and a 9 in one of these 2 cells. And that's our first digit. Okay, so there we go. We've got a digit in the grid. Oh, right. We could have got an easier digit, which I've only just noticed. Where does 1 go in row 1? Well, it's not in those 3 squares. And by symmetry, where does 1 go in column 1? It's not in those 3 squares. So we could have got another digit. Sorry. And anyway, we've got more digits than we know what to do with now. Okay, but what does that mean? I don't know. Maybe now we use the 14 cage, do we? So we now know one, 4, 5, 6 is too many. Yes, I know what we do. Right, let's look at this cage, because this has got to have some low digits in it. The question is how many low digits. Now it's clearly not got 1, 2 and 3 in it, because that's going to put 1, 2, 3 there by Sudoku, and 1, 2 and 3 do not add up to 14. So, this cage does not have 1, 2 and 3 in it, but it must have 2 of the low digits in it. Because if it doesn't, if it only has 1 low digit in it, and by low digit I mean a 1, 2 or a 3, then the minimum this cage could add up to would be 4, 5 and 6 plus a 1, say. Well, 4, 5 and 6 is already adding up to 15. So there are 2 low digits in this cage, and those two low digits are going to marry up with those 2 low digits, or 2 of these 3 low digits, and end up in the 14 cage with one other cell. So you can never, you can never allocate a 1 down here with a 2 or a 3, because the other digits won't work. This has got to be a 2 and a 3 in here, and that's got to be 2, 3, 9 now. Now the 9 in box 5 is vertical, so that's not the 9, and that is the 9. Now there's a 9 in one of those 3 cells in box 8. And we've got no coordination yet between... Oh, of course. Oh, goodness me, Simon. Why doesn't my brain connect things up in the right order? Right, the moment we realise that there's no 1 in the 14 cage, we know the contents of the 14 cage. It's got to be 2, 3, 4, 5. It's the only way it can be done. And that coordinates the 4s and the 5s, look. So now where do 4 and 5 go in this column? Well, they must go in the 16 cage along with a 7 by the power of maths. Now there's a 7 in one of those cells. That's not a 9 now. Oh, okay, so we get... Oh, that's weird. Okay, sorry. So we get a 9 here as well. So we did end up with double 9 here, even though the 9 in this box wasn't in the cell I thought that was going to force that conclusion. Okay, well that's fine. That's forced a 9 here by Sudoku. How many 9s have we done? We've done 4, and we've approximately placed 3 more. Well, 4 more if you count that one. Okay, so we've got to do what now? What's the next stage in our quest to understand this puzzle? It is to allocate. I don't know what it is. I'm just gibbering. I've no idea what it is. Can that be a 7? That would force a 1-3 pair here. Looks maybe possible. We've got to put a 1. Actually, 1 in column 6, look, has got to be in that domino. Oh, yes. All right, hang on. Let's not do it that way. Let's use both of these. So 1 in column 6 and 1 in row 6 is a very nice question to ask, because the 1 in row 6 is in one of those 3 cells, and the 1 in column 6 is in one of these 3 cells. The only cell that meets both of those criteria is this cell, so that's a 1. Yes, that is the world's most unfortunately useless digit, I think. Okay. Come on, Simon, what do we do next? There's got to be some low digits in that 12 cage. Actually, yeah, maybe that's a sensible question. What about this column then? So this column needs 2, 3, 6 and 8. So that's only... Ah, yeah, there we go. That's only a 6 or an 8 because there's a 2, 3 in its box. Now that can't be an 8 because that would be a 1-3 pair to make 12, and there's already a 3 in this box. So that's a 6. Now we know the top 3 digits up there, which are 2, 3 and 8, which is nearly useful. Those digits are now also known. They are a 6, 7 pair, beautiful. So that's a 7. That's a 2, 3. That becomes an 8. This becomes a 2, 3 pair. These 2 squares are now exactly equal to a 7, 8 pair to complete box 5. Therefore, we know these 3 digits now, which are 4, 5 and 6. Okay, 4, 5 and 6 go in there. There's a 4, 5, 6 triple in this column, so those squares are 7 and 8. So this is a very high digit now in the 11 cage. So that's either a 1-2 pair or a 1-3 pair. There's definitely a 1 in this domino. So this square is not a 1. And yeah, okay. And look at column 5. We've got a 1, 2, 3, 4, 5 quintuple along with a 9. So that square is a 6, 7 or an 8. And it's not a 7. And that's the most useless thing that could have been ruled out from it, because we've got an unresolved 6, 7, 8 triple as a result. Okay, now what about this 6 then? So these 2 squares add up to 6 and they're not 2, 4. So that's a 1, 5 pair, which means they're not 5, that's not 1. Beautiful. I've got a 2, 3 pair in column 3 now, so that's a 1. I've got a 2, 3 pair in column 2 as well. Okay. I imagine it's either going to be... In fact, I'm not even going to say what it's either going to be, because I'm going to get it wrong, and it's going to make me look a bit daft. What is it now that we do next? Is it something... I think it's either this box. I wasn't going to say this. The 30 cage can't contain a 5, look. Because the 5's here and the 5's here, so there's no 5 in there. Oh, no. There's no 9 in it either. Whoa. So how on earth do you get to 30 in 6 cells with no 5 or no 9? 8, 7, 6 is 21. You need 9 more without using 5. 2, 3, 4. Right, we now know what is in this cage. This cage is 2, 3, 4, 6, 7, 8. That's an immense amount of pencil marking. Those are not 2, 3. Those can't have a 4 in. So the 4 is in in this domino because of the 4 up here, and this is not 4. Ah, that square's not 7 or 8, look. So that one's become 2, 3 or 6. Can't see what that means. Ah, there's a 4. Oh, have I made a mistake? No, I haven't. Sorry, I thought I made a mistake. But look, what I hadn't noticed is I've got a 4, 5, 6 triple in row 3 now. So that square's a 1. It doesn't seem to do anything, but what it might do is allow me to eliminate 6 from those squares. So we're getting somewhere now. 4, 6, 7, 8, 9. So that square is also 4, 6, 7 or 8. Don't know why I said 9 there. The 9's down here. 4. That's 4, 6, 7 or 8. Golly, that's not 6. And that's not 4, is it? We know the 4 is up here. So that's not 4. Oh no. I think I got to the summit and then I've got stuck on the descent. What does this mean? Maybe we've got to look. So probably it's this 4, 9. I've got to. No, that's still not doing anything. 6, 4, 5. Ah, okay. Right, that's rather beautiful as well. Gosh, this puzzle is really clever. Okay, this square here can't be a 6. Because if you make that square a 6, you can't put 6 in row 4 anymore. Because the 6 would rule itself out of this square by Sudoku, and you can't repeat the 6 in a cage, so it also gets removed from those two as well. So you would rule 6 out of all of those squares, and now I don't think you can do anything in that row. So that is not 6, that's a 2, 3 pair. That means that's not a 2, 3 pair. So that's a 7, 8 pair. Which means that's not a 7, 8 pair. Right, this is down to 4, 6 now, which means that's not 6. It's not doing anything. Now that's not 4. 2, 3, 5. I don't believe it. Oh, I've got a 7, 8 pair here though now. Ah, yeah, okay, that's good. Right, I've got a 7, 8 pair in column 7, so this 13 cage is now 4, 9, because it can't be 5, 8 or 6, 7. And that does give us that top digit as a 5, therefore. So, is that doing anything extra or not? Oh, that 5 is giving me that 5 and that 1. Yes, it is. That's not a 9 either. So I've now got... Now, where do I put 6 in the column? I can only put it here, and that's interesting for that 13 cage, which now has to be 5, 8, and there's a 5 there. So that's 5, that's 8. We can get rid of 5 from this square. We can... Oh, we can do the maths. We can do the secret. Because we worked out those two squares added up to 9, didn't we? And now I've got one of them. I can do that. That's a 3. So that's not a 3. These squares have now got to be 1, 2, and 7, I believe, to make the whole box add up. It's still being recalcitrant, isn't it? That square's a 2 or a 3 by Sudoku in this row. And there's a 3. Good. So that's 2. That's 3. That's 2. That's 3. That 3 is giving me a 2, a 9, and a 3 here. Come on. Keep going. What's that doing then? What are those squares? Oh no. I was about to say something that would have been inept. I think they're a 1, 6 pair, aren't they? So that's not a 6. I don't know what that does. Get rid of the 4's pencil marked in here and take another step. Right, 9 goes here. Okay, so we've got 9, 4, 4, 6, 6, 1. And that means what exactly? This is a 7, this is an 8, this is a 7, this is an 8, this is a 7, That's a 1-2 pair at the bottom of the grid, and suddenly we're getting somewhere again. Come on. That 7 is doing some stuff over here with 7s and 8s. Now, can we resolve? No, everything else seems to be tied up. Okay. What about this? It's probably going to be the 33 cage we need to look at next. Just trying to understand that. The other thing that's interesting I've only just seen is I've got a quintuple look in this column. I need 4, 5, 6 and 8. Oh, I see. Right, that square's a naked single. Because it's got to be from the column, it's got to be a 4, 5, 6 or 8, and from the row it's not 5, 6 or 8. So that is 4, that's 7. That's no longer 4, therefore. Oh, this is lovely. Okay, and that's no longer 4 by the method of working through its own cage. So that places the 4, 5 and 6 go in. 4 and 5 go in box 2. 5 can only go in one place in the awkward 14 cage we were grappling with. That's not a 4 anymore. So we've got a 2, 3 pair here. That's got to be the 4. It's still not resolved. Oh, I see. Okay, but let's carry on working now on row 7 again, where we need 1, 2, 3 or 9 into this square, which sees 9, 2 and 3 in the column. So that's a 1, which means that's a 1. Good stuff. Okay, we still don't know that, though, do we? We know that this, by Sudoku, is 2, 3 or 9. How is that not resolved? How is this still being difficult? The 33 cage, therefore, I think is going to be in some way important. It's got a 1 in it now. Does it need to have a 9 in it? If it doesn't have a 9 in it, it would be 8, 7, 6 is 21, 22, and you need 2 more cells to add up to 11, which is impossible. Right, okay, so it does have a 9 in it, which means that square is not 9. 2, 3 pair here means this square has become a 9. I fear that might not do much, though. Is this fear justified? It might be. What do we need down here? We need 5s, 6s. This is a 5 or a 6. And 7 in this column, I believe, can only go into exactly that square. But that's actually not that helpful. So this is 5, 6 or... Whoopsie. Sorry, this is 5, 6 or 8 to complete that column. Oh, no! Right, okay. Well, I'm going to cheat then. Not cheat, but I'm going to do some cleverness again with this square. If this square is a 6, you can't put 6 in that row again, because the 6 rules itself out of its own cage, and by Sudoku it rules itself out of this cell. So we'd get stuck again. So that's got to be 5. That's a 6. That's a 6 now by force. Oh, come on. You're going to stop again, are you? Apparently you are. I don't believe it. I don't believe it. Okay. Well, this 5. No. Okay, this 5 is seeing itself. So that's 8. That's 5. And that is doing some stuff, look. That is doing some stuff. Yes, come on. This 1, I could have done that before. We did it the hard way. That seems to be ever thus with me. So what have we got in this cage now? We've got 10, 18, 27, and we need another 6. So there's a 6. So it's a 6-9 pair, which gets us the 6-7 at the top, which gets us the 7 and the 8 here. Now this cage is forced to be a 3-2, and look, it's going to unwind. It is going to unwind, isn't it? And that should be an 8. And we've done it. We've scaled it. Not only have we scaled it, we've got down as well. What a brilliant puzzle that is. Absolutely sensational, Clover. A killer Sudoku with logic I'd not seen before. That is a rarity indeed. That's beautiful. It really is. Good grief. I mean, let me just try and articulate what we found here. So, yeah, it was very misleading at the start. I thought we were going to have to climb Everest, and I thought once we focused on these cages, I was convinced it was going to be something to do with that cage and how it interacted with these yellow cells. But it's not. It's all to do with how these yellow cells interact with the red cells and allowing us to realise that there was a repeated low digit in yellow and that digit had to be a 1. And from there, I'm not saying the puzzle became easy. It was far from easy, but it was at least, it felt more approachable after that. Not genuinely approachable, very, very slightly approachable. And we could sort of work on the 14 cage. Yes, that's right, because I managed to work out there couldn't be a 1 in it because that was going to break this. And then after that, it sort of started to hang together. Brilliant. Loved it. I hope you guys did too. Let me know in the comments, and we'll be back later with another edition of Cracking the Cryptic.